We're going to be taking notes from two sections of the book, and they are 9.5, which we're going back to learn one thing, and then 9.6, where we're learning more about matrices. And I've put the homework above each section, so these are the only two homework problems that are from this one topic from 9.5. And if you flip the page and look at the 9.6 notes, there's a set of homework. Actually, I'll flip and show you that. And after each several problems, I've written a super abbreviated description of the topic they relate to, in case you'd rather write down one topic in the notes and then pause and go do their homework on it. You have that option. So the topic in 9.5 that we're going back to is we're planning to calculate the inverse of a matrix of size 3 by 3 by hand, and previously we have done it in the calculator. So this is how we're going to do this. So the first thing we do is we construct a matrix that's wider than the original matrix. So our originals are going to be 3 by 3, and then we're going to make it twice as wide. So we add extra columns on the right, and the left hand side is going to be the original matrix, and the right hand side is going to be the identity of the same size. So there will be ones on the diagonal and zeros above and below. And then we're going to use elementary row operations, which we learned about before, to change the left hand side into the identity matrix, which means ones on the diagonal and zeros above and below. And it will be in reduced row echelon form. This will cause the right side of the matrix to become the inverse of the original. So we are going to find the inverse of this matrix. So the first thing we have to do is construct a matrix that looks like this. So we take this matrix and put it on the left, and we make it wider for a size of a 3 by 3 identity in the right of the same matrix. So it's going to look like this. So I've got my A matrix on the left, and I've got an identity 3 by 3 on the right, so ones on the diagonal and zeros above and below. And then I'm going to do row operations with the goal of getting ones on the diagonal and zeros above and below on the left, and we'll just see what happens on the right. And I have a really specific strategy for this, so that the subsequent steps that I do don't undo the work that I did in the original steps. So the strategy is to get one column at a time. So I'll start with the first column from left to right. And then in each column, when we're working on it, first we're going to get the 1 where it goes, and then zeros below only. And after I've done that for all 3 columns, the last thing we're going to do is to get the zeros above. So I'm going to start in column 1, and my goal is to get the 1 where I want it to be, which would be there for the identity. And luckily, there's already a 1 there, so I can move down the column and work on getting a 0 in that position. So in order to get the 0, I'm going to have to do a row operation. So the row operations you're allowed to do are you're allowed to swap rows. That won't help because I don't have a 0 somewhere else. You could multiply a row by a constant. Won't help. If I multiply by 0, I lose all the information in that row. Or I can add a multiple of another row to a row. So if I take row 2 and I add -2 times row 1 to it, I'm going to get a 0 there. So I'm going to always write mine in the same order here, my steps in the same order. So if I take 2 times row 1 and I add it to row 2, and then I put it where row 2 goes, that will get me a 2 there. So I'm only changing row 2, but I'm using row 1 to do it. So I'm going to talk us through the first one, and then I'll just trust that I did these correctly, which actually I verified on a calculator, so I wouldn't have a mistake here. So -2, sorry, that was a -2. I may have been saying positive, but it is in fact a negative because I need to add to 0. So -2 times 1 is -2, plus row 2 is 0. So that gives me the 0. I guess I'll talk through one more. -2 times -2 is 4, plus -3 is 1, so I get a 1 there. And then I continue to do the same operation on every entry in row 2, and I get that. We only changed row 2 because we put our results in row 2, so notice row 1 is the same, and row 3 is the same. So now we need to think about what we need to do next to get the next thing. So I'm still in column 1. I have a 1 where I want it, I have a 0 below, so I need another 0 below here. I'm going to do the same thing, so I'm going to need to multiply row 1 by 3 and add it to row 3 and put it into where row 3 goes. So that would be 3 times row 1 plus row 3, so that would be 3 times 1 plus negative 3, and that gives me a 0. I'm putting it into row 3. And then 3 times negative 2 is negative 6, plus 6 gives me 0, and I put it there. Negative 4 times 3 is negative 12, plus 15 is 3. That gives me this position. And I continue through the rest of the row, and the rest of my row becomes 3, 0, 1. So I have finished column 1. Then I move over to column 2, and the next objective is to get a 1 in the position I want. So the position I want a 1 is in the middle because the 1s go down. So I want a 1 right there, and luckily there is a 1 there, so that's fabulous. I don't have to do anything. And then I get zeros below. And oh my goodness, good luck. I already have a 0 below just by luck, because sometimes that happens. So actually column 2 so far took care of itself. So now we're going to move over to column 3, and I want a 1 where I need it. So the 1 in column 3 is going to go on the bottom right. So that one's relatively easy. All I need to do is multiply this row by a third. So I'm going to take 1/3 times row 3 and put it into row 3. So the bottom row would be 0 times a third is 0, 0 times a third is 0, 3 times a third is 1, 3 times a third is 1, 0 times a third is 0, and 1 times a third is a third. Fabulous. Now let's see what we're going to do over here. So I have my 1s on the diagonal and the 0s below. So I'm doing the last thing, which is to get 0s above, and I am still going to go columns left to right. So I want to get the 0s above here. So I want to get, let's see which one I did first. I did the first row. Good, I'm doing them in a logical order. So let's get a 0 in this position. So I can use the 1 here, this row 2, to get a 0 there. So if I take 2 times row 2 and add it to row 1 and put it into row 1, that will get me a 0 there. So 2 times row 2, so 2 times 1 plus row 1 negative 2 gives me 0, and I put that into row 1. So that's what I get there. And let's check that it didn't mess up this one. So 2 times 0 plus row 1, 1 gives me 1, and I put it into row 1. Good, it didn't change that. Okay, so I do this operation all the way across the row, and I get a 0 here, negative 3, 2, and 0. And these two rows didn't change. I only changed row 1. So I have only one step left, and I'm working on, lucky I only have one step because I luckily got a 0 there in the process, right? It didn't originally have a 0 there, so that was really nice. So now all I need is a 0 here in that position. So I'm going to use the 1 in the third row. So if I multiply row 3 by negative 2, so negative 2 times row 3 and add it to row 2 and put it into row 2. So that should give me, so I'm going to take negative 2 times 1 plus row 2 is 2, gives me 0, and put it into row 2. There. And trust me that I did the work to get those. Let's just check that I didn't mess up these entries. So if I do negative 2 times 0 plus 0, I get 0. Okay, good, that didn't change. Let's check my 1. Negative 2 times 0 plus 1. Put it in there, I get a 1. Oh good, that worked out. All right, so we finished it because the left-hand side is the identity. 1's on the diagonal and 0 is above and below. So the right-hand side is going to be the inverse. So this is A inverse, and it equals negative 3, 2, 0, negative 4, 1, negative 2 thirds, 1, 0, 1 third. And there's at least 2 ways you could check. So if you want to pause and check, you could put A into your calculator and then use the calculator button to find the inverse, and that would work. Or you could do A times A inverse, and if you do that, hopefully you should get an identity matrix that's 3 by 3. I thought you might like to learn how to do some of these row operations on matrices with the calculator, because it's pretty easy to make a mistake, especially when you do multiple row operations and then you don't get to the right answer. So the calculator offers 4 row operations, so I'm going to walk you through each one. So one possibility is you can swap some rows. So I entered a really simple matrix into my calculator already, so I let matrix A equal this 1, 2, 3, 4, 5, 6 matrix, and then this is row 1 and this is row 2. So I'm going to swap the 2 rows. So we're going to first go into the matrix menu, so second and inverse to get matrix, and I want to go to the math to get the operations, and it's way below the screen, so you can either arrow way down or you can go up and it'll bring you to the bottom. And I'm doing row swap, so that's the one I want. Hit enter, and here's the syntax. I wrote it down for you. First you put the matrix and then one of the rows you want to swap and then the other. So I have to go back to the matrix menu, grab matrix A, that's the one I'm working with, and then you put a comma, and there's the comma button, and you type in one of the rows you want to swap. Well, I want to swap row 1, and then another comma, and then I want to swap row 2, so I'm going to type 2, close the parentheses, hit enter, and look, it absolutely swapped the 2 rows and displayed them there. Great. So now we're going to look at a different row operation. It says row plus in the calculator, and it adds the rows you choose and it puts them into the second row that you enter. So I'm going to take my matrix and I want to add the 2 rows and I want to put them into row 2. So it puts them into the second one that you enter. So I'm going to go back to the matrix menu and math, so I get the options. So you could go down, but I'm going to go up, and that brings me to the bottom. So I'm going to do row plus, that's the one I'm demoing, and the first entry is going to be a matrix. So again, matrix menu, choose my matrix, comma, and then I'm going to take row 1, so comma, add it to row 2, 2, comma, and it always puts it into the second one you entered, so close it. So notice it did in fact add these 2 rows and replace them into the second row. Fabulous. Alright, now let's look at the next row operation. This is star for multiplication of a row. So that just multiplies a row by a factor and then replaces the same row with it. So let's do that one. So second matrix, math menu. I'm going to go up because I got to get to the bottom, and I want star row, so multiply row, so that's letter E there. And the syntax is the factor I want to multiply by, so let's say I want to multiply it by 3. So that's what I'm multiplying by, comma, and then I need to tell it which matrix, so I go back into the matrix menu and select my matrix, comma, and then the row I want to multiply it by, so let's say I multiply it by row 1. So it's going to multiply row 1 by 3 and put it into row 1, and look, it did. Fabulous. Okay, there's just one more. you could multiply a row by a factor, add it to another row, and put it into that row. So the syntax is the factor you're going to multiply by, the name of the matrix, the row you're going to multiply by the factor, and the row you add it to, and it always goes into the last row you list. So let's find this one. So again, I have to go to the matrix menu, math, and then I'm going to arrow up to get to the bottom, and it's star row plus with a parenthesis, so I choose that. So let's say I want to multiply a row by a -1, so it's really obvious what I did. So -1, and then I have to choose the matrix, so back to the matrix menu, select my matrix, comma, and then I'm going to multiply row 1 by -1. So I'm going to enter 1 for row 1. My only other row is 2, so I'm going to add it to row 2, and it always puts it into the last row that you stated. So I'll hit enter. So let's verify that this makes sense. If you look back at my original matrix, I multiplied the first row by -1, so I'll just write it here so we can see. That would make these negative. And then I add them together. 4 minus 1 is 3, 5 minus 2 is 3, 6 minus 3 is 3, and I got all 3's in my second row. So I hope that's helpful. And now let's go back to the notes. So now we're going to work on the topics from section 9.6, and there are several of them. So we're going to calculate determinants, which we don't know what they are yet, for matrices of various sizes with a calculator and by hand. Use it to determine if a matrix has an inverse, and then we're going to learn Cramer's rule and use it to solve a system of equations. And again, a reminder that I have grouped the homework from this section into topics. So if you want to stop after each topic and do the homework, that's an option. So this first thing we're going to do is find the determinant of a 2 by 2 matrix. So if I have this matrix A, the 2 by 2 is relatively straightforward, and in fact you've already done this piece of it in an inverse. So the determinant of a matrix, which can be written as det parentheses the matrix, or the absolute value symbols around the matrix, or the absolute value symbols around the matrix written out. So it would be the product of the diagonal from top left to bottom right, subtract the product of the diagonal along the other diagonal. Too many diagonals in that sentence. So let's find the determinant. Absolute value bars in matrix land mean determinant. So I'm going to try to use a bunch of notations here. So determinant of matrix A, in this case, is going to be forward diagonal, 6 times 3, minus the other diagonal, 2 times -3. So that would be 18 plus 6. So that would be 24. Now we're going to learn how to find the determinant of a square matrix. It does have to be square. That's bigger than 2 by 2. And first we have to learn some new vocabulary and calculations. So if A is a matrix and it's square, the minor is the determinant. So the minor is M, is the determinant of the matrix obtained by deleting these subscripts ij, delete the I row and j column of the matrix. And then the cofactor, so capital A, subscript ij, of the element with the same subscript is negative 1 raised to the exponent, that's the sum of the row and the column, multiplied by the minor. So the minor is going to look like a matrix, but it's not just the matrix, it's the determinant of the matrix. So here it is written out in a different way. So the determinant of matrix A, which can also be written with absolute value bars around, the name of the matrix A, or it can be written with the absolute value bars around the matrix with all the entries displayed. And it's the sum of, now notice we're talking about the first row of the matrix. So we take the entry, A sub 1, 1, and we multiply it by capital A sub 1, 1, which is this factor that tells us whether it's positive or negative, and then this determinant of a matrix that's called the minor. So we're going to do this on this example. So the first thing we do, remember we're working on row 1, so we're going to start with this first entry, A sub 1, 1, and we're going to write it out. So I'm doing this. So we have A sub 1, 1, which is 2, and we're going to multiply it by this capital A with the same subscripts, which has this coefficient that tells us whether it's positive or negative, and then this determinant of another matrix. So let's start with the sign. So we have negative 1 raised to the power of, I'm working on A sub 1, 1 here, so it's going to be 1 plus 1, all right? And then I need this minor. So it's described, the minor, as the determinant of the matrix obtained by deleting the ith row and the jth column. So I'm going to delete I is 1, j is 1, row 1, column 1, delete those, and I'm left with this matrix. So that minor is the determinant of this matrix. So I'm going to indicate that it's a determinant by writing it inside absolute value bars instead of brackets. So it's 2, 4, 5, 6. I'm going to write the whole thing down and then I'll simplify. So that was the first term. Now I need to move to the second term in the first column, in the first row, because we're just doing the first row. So in a different color. I'm going to take the second entry in the first row. So that's 3. So that'd be this. So I have plus 3 times negative 1 raised to the, well, that was row 1, column 2. So that would be 1 plus 2. And then I'm going to multiply the matrix by the determinant of the matrix that remains when I cross out row 1, column 2. So that leaves me with these entries for the matrix I'm taking the determinant of. So 0, 4, negative 2, 6. All right, so I'm done with that one. So now I'm moving on to the next entry in row 1, there, and that's A sub 1, 3. So that entry is negative 1, and then I multiply that by negative 1 to the power of 1 plus 3, and I multiply that by the determinant that remains when I delete row 1 and column 3. So that leaves me with this matrix inside my determinant symbol. So 0, 2, negative 2, 5. And now I just have to simplify. So negative 1 to an even exponent is positive 1, so this is a 2. And then to take the determinant of a 2 by 2 matrix I do 2 times 6 minus 5 times 4. I'm going to do it out and I'll just go down. Plus negative 1 to an odd exponent is negative. So this is going to be negative 3. And then this determinant is 0. 0 times 6 minus negative, so plus 2 times 4. Right, now moving on to this one. Negative 1 to an even exponent is positive 1, so I have a negative 1 from this. So negative 1 times 0 times 5 is 0, minus negative 2, so plus 2 times 2. So now I just have to simplify this. So I misplaced my parentheses here because that should have been all one thing. The 2 is multiplied by that entire determinant. So this is 2 times 12 minus 20 minus 3 times 0 plus 8 minus 1 times 0 plus 4. So this works out to be 2 times negative 8, which is negative 16, negative 3 times 8, which is negative 24, negative 1 times 4, which is negative 4, and that equals negative 44. So the determinant of matrix A is negative 44. So if you turn the page, we're referring back to the definition of finding the determinant. So that definition found the determinant by expanding the determinant by the first row. You can actually find the determinant by expanding the determinant by any row or column. So we're going to use the same matrix from above and find it by expanding by the second row, and again by expanding by the third column, just to verify that we will definitely get the same determinant. So here's our matrix. I'm going to be a little faster this time. So this is the original matrix A. Now we're expanding by the second row, so I'm working on this row. So the determinant of A, I'm going to take the first entry, so that's 0, and it doesn't matter what my matrix is, that term's going to equal 0, so I'm not even going to bother to write it down. And then I'm going to add the following entry in the second row, so that's 2, and multiply it by negative 1 to the power. So this is row 2, column 2. So this exponent would be 2 plus 2. And then the matrix that remains when I delete row 2, column 2 is 2, negative 1, negative 2, 6. Okay. And now I'm going to move on to the next entry in row 2 and add that, which is 4. And I get negative 1 to the exponent, row 2, column 3, so 2 plus 3. And then the remaining matrix, when I delete row 2, column 3, is 2, 3, negative 2, 5. So now we're going to work this out. So I have 0, that was nice. plus negative 1 to a positive exponent is positive, so 2. And then this determinant, 2 times 6 is 12, minus negative 2 times negative 1 is positive 2. Now I'll move on to this entry. Negative 1 to an odd exponent is negative, so negative 1 times 4 is negative 4. And then I'm going to do the determinant of this, so 2 times 5 is 10, minus negative, so plus 2 times 3 is 6. So I'm almost done. So I have 2 times 10 minus 4 times 16, and that equals negative 44. So that's really nice because that's the same as what we got when we did it with the first row. And now we're going to do the same thing and expand by the third column. So again, I'm going to write down my matrix A. And I'm going to expand by this column. So I'm going to start with my first entry. So the determinant, negative 1 from the entry, multiplied by negative 1 to the power of row 1, column 3, so 1 plus 3. And then the remaining matrix, when I cross out row 1, column 3, is 0, 2, negative 2, 5. And then I'll add my next entry in column 3, so that'd be 4. So plus 4 times negative 1 to the row 2, column 3, so exponent 2 plus 3. And then the determinant of the matrix when I cross out row 2, column 3. So I'm left with 2, 3, negative 2, 5. Almost done. And then I have this last entry here in the column, which is 6. So 6 times negative 1 to the power of row 3, column 3, so 3 plus 3. And my matrix that remains when I cross out row 3, column 3 is 2, 3, 0, 2. And now I'll just simplify. So negative 1 to an even exponent is positive 1, so I get negative 1 multiplied by 0 minus negative 4, so minus negative 4, so that's 4. And then negative 1 raised to an odd exponent is negative, so that's going to be negative 4. And then this determinant is 10 minus negative, so plus 6. And then this term, negative 1 to an even exponent is positive, so this 6 is going to be positive, so plus 6 times this determinant. 2 times 2 is 4, minus 0. All right, so I get negative 4 minus 4 times 16 plus 24, which equals negative 44. Woohoo! Yay! It's the same. So now you have multiple different methods. So you should choose the one that has the fewest complicated calculations, I think. So that was a bunch of determinants if you want to pause and do some of the homework. All right. So here is how you can find out if a matrix has an inverse without actually calculating the inverse. So if A is a square matrix, remember that it won't have an inverse if it's not square. Then A has an inverse if and only if the determinant of A is not 0. Or in other words, if the determinant of the matrix is 0, it does not have an inverse. So this one is bigger. So we're actually going to find the determinant of this 1, 2, 3, 4, 1, 2, 3, 4, 4 by 4 matrix. So let's choose a row or column that we think would be nice and easy to expand on. So I'm kind of thinking this row with all the zeros is looking really good to me. There's a column that does that too, but we're going to expand on this row. So expand this row. So this entry, 0, times the matrix, it doesn't matter what it is because 0 times anything is 0, plus this entry, which is 0, times, doesn't matter what this is because it's going to equal 0, plus another 0 times a determinant that doesn't matter what it is because I'm going to get 0. All right, this is the one that's going to matter. 3 times negative 1 to the power of row 2, column 4. So x1 of 2 plus 4. And then the matrix that's left when I cross out this row and this column, 1, 2, 0, 5, 6, 2, 2, 4, 0. Okay, great. Let's simplify this so that we can go forward. These were all zeros. Negative to an even exponent is positive, so I get a 3. So this is a 3. Okay. So I have 3 times the determinant of this matrix. And now I've got to find the determinant of this matrix. So I can choose any row or column. So I'm going to expand this row with all the zeros. Sorry, column. This column. Yes, okay. So don't forget to keep the 3. Alright, and I'm going to give myself brackets. So this entry is 0 times the determinant that it doesn't matter because it's going to be 0. And then this entry is going to matter because it's non-zero, times negative 1 to the row 2, column 3. So the exponent is 2 plus 3. And then when I cross out row 2, column 3, I'm left with 1, 2, 2, 4. And then I've got one more entry in this column, which is 0 times the matrix determinant, doesn't matter what it is because I'm going to get a 0. So that's 0, this is 0, so my answer is going to be this, and don't forget the 3 in front. So I have 3. Negative 1 to an odd exponent is negative, so this is going to be negative 2. And then this determinant, which is 4, 1 times 4 is 4, minus 2 times 2, which is 4. All right, so I have 3 times negative 2 times 0. So that would be 3 times 0, which is 0. Woohoo! So the determinant of B is 0. So we found the determinant, but the question was, does it have an inverse? B does not have an inverse. And that's because the determinant of B is 0. So now let's see. If we have a matrix A and it's square, and the matrix B is obtained from matrix A by adding a multiple of one row to another row, or a multiple of one column to another column, then the determinants of those are the same. So that tells me that if I have a really messy, if you will, looking matrix and I need to find the determinant, that I have the chance of making it simpler by using this theorem. So I'm going to look at rows and columns and see if adding multiples of them will get me some zeros, because we noticed before that if we got a bunch of zeros, we would be able to find the determinant more easily. So let's see. I'm noticing that row 1 and row 3 look like a lot of the entries have common factors. So I think if I take -3 times row 1 and add it to row 3, I'm going to get some zeros in some places, so let's try that. -3 times row 1, and I'm going to add it to row 3, and I'm going to put it into row 3. So that's going to give me, so 24 minus 3 times 8, I'm putting in row 3 here, right? Just row 3, and then I'll fill in the missing things. So that's going to give me a 0. -3 times 2 is -6, plus 6 is 0. Put that into row 3. -1 times -3 is -3, plus 1. It's actually +3, plus 1 is 4, so this is 4. And -4 times -3 is +12, plus 12 is 0. Okay, now I'm going to put the other 1, 2, 3 rows back in here where they were. 8, 2, -1, -4, 3, 5, -3, 11, so second row, and then the last row, 2, 2, 7, -1. So we were able to transform the third row into a row having 3 zeros in it. So now, this is not C anymore, so let's call it D. Okay, so the determinant of D is equal to the determinant of C by this theorem. So I can work on this determinant. So if I expand on row 3, I have 0 times the determinant, doesn't matter what it is, plus 0 times another determinant, doesn't matter what it is, plus 4, this is the one that matters. So if I cross out row 3, column 3, I'm left with 8, 2, -4, 3, 5, 11, 2, 2, -1. Okay, and then I have another 0 here, so plus 0 times, doesn't matter what it is because it's going to be 0. So this is also not a lovely matrix. This is all we have left because everything else here was zeros. So let's see if we can do the same thing. So it looks to me if I take row 3, multiply it by -4, and add it to row 1, I can get some zeros. So I'm going to do -4 times row 3, add it to row 1, and put it into row 1. And I'm not going to forget that I have this negative, no, it's +4, sorry, +4 in front of there. Okie dokie. So -4 times 2 is -8, plus 8 is 0. -4 times 2 is -8. Plus 2 is -6. And -1 times -4 is 4, plus 4 is 0. And we didn't change any other entries. So if this we call matrix, I'm up to E, I think, then this would be matrix F, which is equivalent to matrix D. All right, the determinant, not the matrix, the determinant. So now I can expand on this row. So I'm not going to forget the 4, that was the coefficient, and I'm going to expand on this row. So I have 0 times doesn't matter, minus 6 times it does matter, so row 1, column 2. So I need a negative 1 raised to the power 1 plus 2, and then the determinant of the remaining matrix, which is 3, 11, 2, negative 1. All right, so I have 4, that's a 0, negative 1 to an odd exponent is negative, times negative 6 is positive 6, and then the determinant of this matrix is 3 times negative 1, so that's negative 3, minus 2 times 11, which is 22, so this is 4 times 6 times negative 25, so 4 times 6 times negative 25, so that's negative 600. So look at that. The determinant of the original matrix C is negative 600, so it does have an inverse because it's non-negative. So now we're going to work on Cramer's rule. So note there's a really nice proof in case you want to look at it. It's actually really good to have a look. So if you have a linear system, linear equation, two equations, two unknowns, it has a solution. So the solution to the system would be, what does x equal, what does y equal? And remember the absolute value bars mean determinant. So x equals, so what does this look like? Just looks like alphabet soup here, right? So the matrix equation that would represent this system would be matrix equation, right? It would be A, B, C, D, the coefficients from the left-hand side of the equal signs times the solution matrix equals the solutions. Remember this? So notice the denominator are the determinants of this matrix, okay, because absolute value bars mean determinants, and the numerator is close but with a little change. So x equals, and then the right-hand column is the same, and the x column, if you will, got swapped with the solutions. And then the y value, the denominator, is this matrix, and the numerator is almost the matrix, but the y column is swapped with the solutions. And this is only true if the determinant is not equal to 0. So that's how you do it. We're going to find it. This is the same thing written in a different notation. So D is this matrix, right, that came from the left-hand side of the equations, the coefficients. And D sub x is this matrix, but D represents the determinant, okay? And notice again, the first column, the x column, got swapped with the solutions, and likewise for the subscript y. And then, sorry, D was the matrix. And then the absolute value bars mean determinant. So this is just a different notation. So the same thing written twice. So now we're going to do an example. All right, so here's a system. We're going to use Cramer's rule to solve the system. So let's first write the matrix that corresponds to the coefficients of the left-hand side. So that would be 2, 6, 1, 8. and I'm using the second notation. And then the matrix that corresponds to the x coordinate, I would replace the x column with the solutions, so those would get replaced with -1, 2, and the y column remains the same. And then d sub y is another matrix where I start with this, and I leave the x column as is, and I replace the y column with the solutions. The solution column, if you will. And now I'm ready to find x and y, but I'm going to calculate the determinants first. So what's these are all squares, so it's relatively simple. So the determinant of d is 2 times 8 minus 1 times 6. So that's 16 minus 6, which is 10. And the determinant of d sub x is -1 times 8 minus 2 times 6. So that's -20. And the determinant of d sub y is equal to 2 times 2 minus -1 times 1. So that equals 5. So now I know what those are. So remember, x equals, so the x value in the original equation, it's the determinant of d sub x divided by the determinant of d. So that would be -20 over 10, so 2. And y equals determinant of d sub y over determinant of d. So that would be 5 over 10, so 1/2. So the solution to this equation is x equals 2 and y equals 1/2. So we did that for the 2 by 2 matrix. And now we're going to expand that to a matrix of any size. So using the same notation, but instead of x, y, z, and then we ran out of letters, we're going to go, the x is the solutions. So x sub 1 would be like x, and x sub 2 would be like y, and then as many as you have rows in the matrix. And the numerator is the determinant of that matrix where you replace that column with the solutions divided by the determinant of the left-hand side coefficients of the equation. So these are all the same. So we're going to do the same thing to solve this system. So this one is going to be, well, let's write it as a matrix equation. D is going to be 2, -3, 4, 1, 0, no y term, 6, 3, -2, no z term. And then it would be times x equals solutions. So these are the solutions. So d sub x would be, I replace the x column with the solution, so 1, 0, 5, and then I leave the other two columns the same. D sub y, I leave the first column the same, replace the middle column with the solutions, leave the last column the same, and d sub z, I leave the first two columns the same and swap the last column with the solutions. Got a little sloppy there, but I hope you can tell what I wrote. And now we're ready to find the solution. So we need the determinants of all of these. So I think we might all be getting kind of tired of finding determinants by hand. So I'm going to show you how to do it in the calculator right now. So the determinant of x. Actually, I'll write the other notation because that's what it says in the calculator. So the determinant of matrix D. So let's put matrix D in my calculator. And I'm going to put it into D because that would make sense. And D is a 3, oops, sorry. I need to edit. It's a 3 by 3. So I need to make sure it says 3 by 3. And then I'm going to put in my entries. And then I'm going to leave that screen. Oh. That was kind of weird. Makes me feel like maybe I didn't actually edit my matrix. Okay, that was weird. I'm going to try again because evidently I didn't actually edit it. Three by 3. Maybe that's where I went wrong. Okay. Okay, that looks better. So let's look at matrix D, make sure it's what I wanted. Oh, thank goodness. All right. So I want to find the determinant of that matrix. So I'm going to go into the matrix menu, and I'm going to go to math, so I have options. And look, it's the first one. It's DET for determinant. And now I have to tell it which matrix I want the determinant of. So I'm going to grab matrix, arrow down, and choose D because that's where I put it. And look, it says it's negative 38. So the determinant of matrix D is negative 38. So now you know how to do it. You can do it for the other 3. So let me just tell you what they are. So I'll write it this way for the fun of notation. The determinant of D sub x, which you would have to put it into your calculator to find it, is negative 78. And the determinant of D sub y, that's a y, is negative 22. And the determinant of D sub z is 13. So the solutions to what are x, y, and z? X is equal to D sub x determinant over D, so negative 78 over negative 38, y magnitude of D sub y magnitude of D equals negative 22 over negative 38, and z equals magnitude of dz over magnitude of, sorry, I'm saying magnitude, it's determinant, which is 13 over negative 38. So x equals 39 over 19. Aren't you glad we didn't have to do that by hand? And y equals 11 over 19. And z equals negative 13 over 38. So there you have it. Kramer's rule. We solved this system. Fabulous. We have only one more topic. You might want to stop and do the homework on this one. So the very last topic is using matrices to find area of a triangle in the coordinate plane. So here's the theorem. If you have a triangle in the plane as drawn, and it has these coordinates, so A1, B1, A, 2, B2, I guess I went this way, A3, B3. So these are the vertices of the triangle. Then the area of this triangle, so curly A is representing the area, is equal to this matrix where the coefficient is plus or minus a half. This is the determinant, and the entries are the coordinates of each of the points, and the third column is ones. So we're going to quick do an example and find the area of this triangle. So I need the coordinates of the vertices, and the coordinates are nice integers, so I can just label them. So this is 1, 2, this is 3, 6, and this is -1, 4. So those are my vertices. So the area of the triangle is plus or minus a half, and then I have the determinant of the matrix where the third column are ones, and these are the pairs of vertices. It does not matter what order you put them in, so I'm going to go counterclockwise for no special reason. So -1, 4, 1, 2, 3, 6, and now I have my matrix. And notice we're going to choose the sign that makes the area positive. That means here the plus or minus, so I have to save that until later because I don't know what this determinant is yet. So I have plus or minus a half times that determinant, and we're going to do that determinant with the calculator. So I'm just going to leave that to you. So type the calculator in, choose the determinant option, and find out that that determinant in fact equals -12. Woohoo! So I actually am going to have to choose the -1/2 in order to make the area positive. So that would work out to be 6, and that is the area.